So thank you for the introduction, and I first would also like to thank the organizers for the opportunity to present our work here. My colleague Martin Neukomm and I represent the company Fluxim, and you've probably seen us outside at the booth, and if not, you're welcome to look later. We're still there to show our measurement setup and also the simulation software. And
I'm afraid we will have to upload this again because
the main reason I'm here is because I'm doing a PhD on degradation mechanisms in organic electronic devices. The PhD is supervised by Professor Uli Lemmer in Karlsruhe and Professor Beat Rustaller in Winterthur, and it's done in a close collaboration with the company Fluxim. So I can use all the tools that Fluxim offers, and I would shortly like to introduce these tools. Some of you might already know the simulation software ZFOS, which is a 1D fully coupled optoelectrical drift diffusion simulation that allows you to model absorption and also electrical characteristics of organic solar cells and OLEDs. And you can actually model steady-state transient and impedance experiments with this software. And ZFOS has been commercialized already 10 years ago, so it's some kind of anniversary this year. And then there's the second product, PIOS, that you can see outside, which is a measurement platform. We call it all-in-one characterization because it can do a lot of different electrical techniques in one single setup. So again, you can do transient, steady state, and impedance characterization of your devices there. So I will really focus on these complementary electrical techniques and try to show you how you can investigate degradation using this. I would now like to propose a procedure how you would investigate degradation. So of course, after you have chosen the aging conditions, you will characterize your device using a lot of different techniques. In our case, we use a lot of different electrical techniques. And so you do this characterization during the degradation time as often as possible, so you have a very consistent and systematic data of the same cell during degradation. Then if you look into the different measurements, you can probably directly only with the eye see what happens inside your device. You can investigate the shapes of the different transient curves, and you will find already some parameters and can analyze already how some parameters behave during degradation. So you can directly, just from the experimental side, try to identify possible mechanisms or exclude other mechanisms that they are not happening. And then you start doing the simulation. So as I said, it's a drift diffusion simulation that we use, and we can actually simulate all the different measurements we have just done with the setup. And that means in the end we can end up with a single set of parameters that can describe all the different electrical techniques, and that is valid for the specific device or material combination. And using this, you can then validate a proposed degradation mechanism. So I think I want to go through this procedure now with the study that I did. I'd like to introduce the study. This is a collaboration with CSEM in the Swiss project Dursol, and we focus on really standard OPV, standard geometry, standard materials. We have P3HT, PCVM. And in the first part of the study, we varied the whole transport layer to see its influence on the stability of the device. So we use P.PSS, but also different solution processed metal oxides, in this case molybdenum oxide and vanadium oxide from two different precursors. And all the devices we investigate are unencapsulated. So you will see it's quite quickly degrading. And we have three different aging conditions. So the first one is just in air, at 25 degrees and 45% humidity. The second one is at enhanced humidity of 75%, and the third one was done in a climate chamber for an accelerated aging study where we have 45 degrees Celsius and 85% relative humidity. Here you see the degradation kinetics of the short circuit current in these 3 different studies and for the 4 different whole transport layers. And of course what you will see on the first glance that the p-dot cells behave worse in terms of stability. You have a very fast degradation. So we already can identify p-dot as the mainly responsible material for the degradation that is going on in this process. And there's already a theory about, which has been published some years ago by Esther and her collaborators, because the water ingress, so we are working in air or in humid air, so the water ingress through the hygroscopic p-dot will actually lead to an oxidation of the aluminum cathode. And this is the main degradation mechanism in these devices that is responsible for the loss in short circuit current. So far, I would like to show you some numbers for this. So this is the T80 time for these studies. And actually in this case I extracted the T80 time from a fit with the square root of the degradation time, which means it's a diffusion process of water coming inside the device. You see, perhaps I can go back. So you here already see the fits. It works quite well for these devices, so we can already see that it's really the water diffusion that is depending on the different whole transport layers and which is responsible for the degradation. And what you also see, of course, that if you replace p-dot PSS by these alternative whole transport layers, you will strongly increase the stability by at least a factor of 10, but up to a factor of more than 300 times. And what we also see and can confirm again is that with increased humidity and increased temperature, you will, of course, accelerate the degradation. I would now focus on the accelerated aging study and also on the p-dot PSS device, because in this measurement series we have the whole degradation time range spanned from fresh device to really dead device. And in this case we did a very detailed characterization using the measurement setup PIOS. So you can define a measurement routine with all the different electrical techniques. So in this case we had current voltage curves, a small voltage pulse, transient photocurrent, dark and photocoeliph, capacitance frequency, and capacitance voltage. So this whole routine was then repeated automatically. It takes about 5 minutes to do this routine once, and it's repeated automatically during the degradation process. So this gives you a very systematic data set in the end, because it's always the same device that you investigate. It's always the same conditions that you have. And if we look at the measurements, I will try to show you these measurements now. So, of course, the current voltage curve you see. Again, this strong decrease in the short circuit current. I always show the first 2 hours of degradation now. So 120 minutes time, and you see in the degradation is here from 0 to, well, it's 108 minutes. From blue to green, you see you already lose in these 2 hours more than 90% of your short circuit current. At the same time, you see that you don't lose any of the open circuit voltage. This is really stable. You can directly analyze this. When you see that we have such a stable open circuit voltage, we can directly conclude that there's not a big, or that there cannot be a big absorption loss. And secondly, the work functions that are defining the built-in field, they are not changing. So the energy levels of the electrodes are not changing in this time. But of course the main loss comes because we lose injection and extraction efficiency somehow. If we now go through the other techniques, we will find some more information. I would like to show you this voltage pulse experiment, which is a very simple and fast experiment to do, but you still get nice information from it. What we do, we apply a small voltage step in reverse bias, about 100 millivolt step in reverse bias, and this induces only a displacement current step in your device. So it's only a current step that you get, which is inversely proportional to the resistance, and then decays with the RC time. So you can directly extract resistance and capacitance from this. So the resistance you get is actually the resistance of the electrodes, and the capacitance is the geometric capacitance of your active layer. And we see that during these 2 hours, it's totally constant. We have another technique, capacitance voltage, where you can also extract the geometric capacitance in the reverse bias. And if you do so, you will also find the same value and confirm that its capacitance is not changing. So we have already 2 complementary techniques that give us the same information. So we can rely more on these parameters. And secondly, what we see in the capacitance voltage, this peak, which is related to the injection behavior, it doesn't change its position. So it's always at the same voltage, and that means again that the energy levels that are responsible for the injection behavior, that they are not changing during degradation. On the other hand, we see that the peak is decreasing strongly. So again, our injection efficiency is strongly reduced. Then we have the capacitance frequency measurement, where we can investigate 2 features in principle. The first one is this steep slope at high frequency. This is directly related to the RC time. So we have another way of measuring the RC time, and this is, again, it's constant. It's very consistent with the value that we already have from the voltage pulse. And then we have this plateau that we have at low frequencies. And actually, you see it's not totally constant, but there's a slight increase. And this might be related to traps or doping in the device. But on the other hand, you already see it's not changing very much during the degradation. So if there are traps, they will not be the dominant mechanism, because otherwise we would see a much bigger change here. Then I would like to show you the CLIF measurements. CLIF is charge extraction by linearly increasing voltage. That means you apply a negative voltage ramp to your device, and with this you can extract all the mobile charges that are inside. So if you have a device in the dark which is empty, then you cannot extract any charge, and your voltage ramp will lead only to a constant displacement current. And this is exactly what we see here in the dark CLIF curve. So we can already say that we have no doping in the device. We have no mobile charges in the device. And you can also do a photo-CLIF experiment, which means you illuminate the cell before the voltage ramp and then extract all the photo-generated charges. This is what you see in these curves. And here we again see that this overshoot that you get from the charge extraction is slowly decreasing during degradation. It's decreasing by about 20 to 30%. So not as much as the photocurrent itself is reduced. And this is again due to the loss in extraction efficiency. And furthermore, what is usually done, the photo-CLIF is usually done to evaluate the mobility, charge carrier mobilities from the position of this peak. And you see it's not really changing a lot. So you would need a bigger change in order to induce some stronger effects. For example, if you have a very slow, or if you have a mobility that is decreasing strongly, then you would see a much stronger effect in this curve. So we can also exclude that the mobility is dominantly responsible for our degradation. The last measurement I would like to show is the transient photocurrent. I think that's a very interesting one. So here we have just the response to a light pulse. You turn the light on at time 0 and turn it off at time 60 microseconds again. So in the case of a good device, you will have just a monotonous rise of your current, and then it goes into a steady state value, which is exactly the short circuit current that you already have from the current voltage curve. And you can confirm again that the short circuit current is strongly decreasing during the degradation. So that's just the same curve as you've already seen. But it makes a lot of sense to do this technique nevertheless, because you see it's a strong change of the shape in this curve. So you don't just homogeneously reduce the current here, but a strong overshoot is appearing and dominates actually the whole curve. And then it decreases back and goes to very low steady state currents. And you have a second feature, which is this small undershoot here, which means actually that after you turned off the light, your charges are moving back inside the device, which is perhaps not very clear where this should come from. So I think in terms of understanding, this will later be a measure to evaluate an appropriate model. If you can simulate this with your model, then you probably are on a good way to understand the device. But let me first conclude what we already know just by analysis of these complementary measurements. You have already a lot of information available. We know that the electrode work functions that are responsible for the injection behavior and the built-in voltage are not changing. The resistance of the electrode is also constant. The layer thickness is constant. We know that because the geometric capacitance has not changed, and that means that the layer thickness is constant. This is quite an important information, because you might also imagine if you have a water ingress that the layer thickness might expand. This is not the case here. And furthermore, we see that there is no mobile charge, no doping in the device. And we can already exclude some mechanisms. So we can exclude that the decreased mobility is responsible for the degradation. We can exclude that there is an absorption loss which is dominant. There might be some absorption loss, but it's not a dominant mechanism. And also traps cannot be the dominant mechanism, because if these would be dominant, we would not. So from this combination of different experiments, you can already conclude this. And now you can try to start modeling with all these information already available. The first model is quite obvious. As I said, we believe that the water ingress through the p-dot layer will lead to an oxidation of the aluminum. So you can imagine this oxidation layer growing slowly. And in this case, we have a homogeneous degradation of the whole active layer, or active area. If we want to model this, we can simply include this thin layer into our layer stack in the model and include it as an injection and extraction barrier to charges, because that's exactly what we see in the measurement, that we lose extraction and injection efficiency. So if you do this, you can then either vary the thickness of this thin layer, or you can vary the height of this energy barrier. And you will find in both cases, at least qualitatively, the same behavior. So you will strongly reduce the short circuit current in both cases, and at the same time keep the VOC constant. So this is what we saw in the data. On the other hand, we directly see that this strong S shape is not what we have in our measurement. So actually it's not possible to describe the JV curves we have just with this approach. So we have to think of something more elaborate for this special case. And what I would propose is this effective area model. So in principle, if you look more closely to the device, we have water ingress from the sides and also through pinholes in the aluminum. And then the effective area, which is already degraded by the water, this is increasing with time. So you don't have a homogeneous growth of this layer, but in these accelerated conditions, you can actually think of an instantaneous degradation on places where you have water. And that means that you have a lateral degradation, in this case, from the sides, as well as by growth of these pinholes. And this means you lose effective area. You can now think of your device as a part which is like the outer parts, which are already degraded, and you still have a good working subcell in the center. And this makes it now possible to simulate this if we just model these two subcells separately and add them together in a parallel circuit. So we would have the same voltage and the currents will add up. And now I can just add these currents up, weighted by the effective area. So I introduce this parameter x, which corresponds to the part of the active area which is already degraded. And that means x starts at 0 for the fresh device and goes up to 1 for the fully degraded device. So if we do that, we find a very nice quantitative and qualitative agreement. And what I show here is this x going from 0 to 1, and the numbers in between are active areas that are really corresponding to real respective areas of the device that are already degraded. So with this you can directly simulate your JV curves. You see you have this strong loss of the short circuit current and you still keep the VOC constant. And if we now look in this transient photocurrent measurement, you see that it's also working. So we start with a good fit of the fresh device, and now if you introduce this active area approach, you will find that a strong overshoot appears and even this small undershoot is also reproduced. So we can actually really see that with this approach you can re-simulate all your data. If you look a bit more closely into this, we can perhaps even understand better what happens during this transient photocurrent. So we can do this if we have the simulation. So we can look inside the device and, for example, look at the profile of the electron density. In this case, the electron density is plotted here versus the position in the active layer. So in this spot we have the aluminum, and in the degraded device we will have the aluminum oxide interface here. So if you look at the steady state conditions in the dark, so before the light pulse you have actually no charges in the device in both cases. Now you illuminate the device, and in the fresh device you end up with some distribution of quite a low charge carrier density. Because you have a good extraction, you can extract most of the charges. And in the degraded case, you see that we have this strong interface building up. And this leads that there are a lot of electrons piling up here. Because they see the built-in field, they want to go to this side, but they cannot go out. So they will pile up, and also a big space charge is in the whole active layer, actually. And now if we look at the electric field in the device, again in the dark we have just the built-in field, which is very homogeneous. In the fresh cell steady state, under illumination, you get some kind of change in the field which is corresponding to the inhomogeneous absorption profile. And in the degraded case now, we actually have no electric field left. So this huge pile up of electrons screens the whole built-in field. And of course then it becomes clear why we have no current left. If we have no field, there will be no drift possible, and we can have the short circuit current gets really to nearly 0 in this case. Yeah, so I hope I could show you some interesting things. I showed you that with alternative whole transport layers you can enhance the stability of unencapsulated standard OPV devices. We confirmed in these conditions that the main cause of degradation is the water ingress, which leads finally to an aluminum oxide layer that can be modeled as an interface barrier. And in the accelerated conditions we see that this interface layer is not forming homogeneously, but rather as a lateral degradation process. And then we can try to model this with an effective area model, and we could validate this model using different electrical experiments. So in principle, I would really like to, or hope I could show you that this combination of different electrical techniques in measurement and simulation can give a lot more insight in your device degradation mechanism. With that, I'm finished. I would like to acknowledge funding from the Dursol project by Swiss Electric, and I would like to thank my collaborators from CSEM and Fluxim, and I would like to thank you for your attention.
Thank you very much, Simon. Are there questions? I'm looking at Harald. No. Birger?
There are two things which really puzzle me. Is it really a bare aluminum electrode on top, which makes such nice IV curves? It's
Yes.
okay, and we made very similar measurements in the 2005 or 2006 on these inverted devices with this chromium contact, and also P dot on top, where of course you have also a lot of oxygen and water coming in through the P dot homogeneously, and we always observed a very, very high degree of doping. It really surprises me that there's no doping at all in these devices. Is it because the aluminum takes up the oxygen before it can dope the P3H, or do you have any idea about this?
If you look into the measurements at later times, now I only showed the first 2 hours.
Mm-hmm.
If you look at the 3rd hour, you will see a huge doping effect.
Ah, okay.
Which is
so
then the
it's just
dominant
later.
mechanism. So this is happening before that.
Yeah, because for these inverted devices, the doping was the dominant effect, which leads also to this decrease in current.
Yeah, you will see that then.
It's really funny that the signature is very similar.
Okay, further question? Yes.
And you have shown that the degradation mechanism is due to the water diffusion on the side, on the edge. So, and you also show a very nice kinetic and simulation results. So you said this is based on a model. So this is due to the water diffusion. So which kind of water diffusion equation you use for this modeling? Because I think the water diffusion from the side it's very complicated.
I didn't use a model, I just used the effective areas that I get from the proportion of the short circuit current to the original value.
Yeah, I mean the one you do this kinetic degradation, huh?
You could also imagine that this is actually
not this one.
The decrease of the effective area.
I mean, quite earlier slides. Maybe you just go some more slides front.
Okay.
Next one. Yeah, this one.
Is just a fit with the square root of time, and I've not evaluated more.
Yeah, I think the water diffusion from the side is not the same in the bark. Maybe it's different. So.
Yes.
I think that when you do this simulation or do the equation simulation, so the diffusion equation has to be very careful to choose the right. This is my.
Yeah, we haven't done that.
Okay. Final question, Dana.
Just a quick question regarding the so-called space charge buildup. You're saying that you're screening the field in the device and therefore not extracting the carriers. However, when in your IV curves in the experiment, you don't see the carriers come out in reverse bias where the field would be much higher. Do you have any comments or regarding this?
In the IV curve?
Yeah, so if there was a space charge that's built up, you would overcome that by applying a larger reverse bias to the device. And then the photocurrent, if it's there, the carriers would be swept out, but you don't see that. So I was wondering if you could comment on this.
If we go to very high negative bias, we see that we can still extract all the charges. even for the fully degraded cell.
Okay, I think this was the last presentation in terms of the program of the Industry Day. I would like to thank again all speakers, and please join me in thanking them.